Hello, this is Garrett Keane. In this video, I'm presenting the solution to the integration problem which you see here. The equation is a quotient in which the numerator is the linear function minus x plus 26, and the denominator is a quadratic equation x squared minus 7x minus 8. In its present form, it is not possible to integrate this equation directly. The denominator, the quadratic equation, must first be factorized, and then the correct partial fraction rule must be applied to transform the resulting quotient into smaller quotients which can be integrated using the methods which you have applied previously. Our first task is to factorize the quadratic. The method to do this is shown here. We run through the factors of constant minus 8. So our first set here is minus 4 multiplied by plus 2. If you add these two together, you get minus 2. In this, these two will give us the factors x minus 4 multiplied by x plus 2. However, these are not correct because the sum of the factors minus 2 has to equal the coefficient of x. We try out another pair. This time we do the opposite, plus 4 multiplied by minus 2. These add up to plus 2. They will give us the factors x plus 4 multiplied by x minus 2. But once again, they're not correct because the sum of the factors plus 2 is not equal to the coefficient of x. We'll try out another set of factors. This time it's plus 8 multiplied by minus 1. This does give us minus 8. The sum of these two is plus 7. It will give us the factors x plus 8 multiplied by x minus 1. But of course, it's not correct because plus 7 is not equal to the coefficient of x. So we will get our answer when we swap these around. We now have minus 8 by plus 1. It does add up to minus 7, so this is the correct one. And it gives us the factors x plus 8 multiplied by x plus 1. Here we see that the original quadratic in the denominator is now replaced by the two factors x minus a multiplied by x plus 1. The next step is to choose the correct partial fraction transformation rule to separate these denominator into two separate quotients. As we saw on the previous page, our function now has two factors, linear fractions, in the denominator, so the correct equation to choose is the first one in this list. In this slide, we present the general solution to a problem of this type. We have the integral of large A, the arbitrary constant large A over x plus A, plus the integration of large B over x plus B, where large B is an arbitrary constant. In the next step, we take large A and large B outside the integral. We're now in a position to integrate these. The integral of 1 over x plus A is the log of x plus A, and the integral of 1 over x plus B is the natural log of x plus B. In the next stage, we basically use one of the rules of log functions that says that we can bring this constant here up as the power here. So a times the log of x plus a is equal to log of x plus a to the power of large A. And the same applies here. B times the log of x plus b is equal to log of x plus b to the power of b. And then what we can do is we can use the rule where the sum of the logs is equal to the product of the logs. So this now becomes the log of x plus a to the power of large A multiplied by the x plus b to the power of large B. So we've amalgamated two separate logarithmic functions into a single logarithmic function. Back to our original function, we split the quadratic into two factors. We've selected this rule from the partial fraction transformation rule, and we apply this rule to our problem above, and that tells us that we can split the quotient here into two separate smaller quotients, where we introduce the arbitrary constants large A and large B. Is to transform the quotients in the equation on the previous page into products, and we achieve that by multiplying each term in the equation on the left-hand side and the right-hand side by the denominator of the left-hand side. You can see here straight away that these are going to cancel. So on the left-hand side, we're just left with the original numerator, minus x plus 12. On the right-hand side, the first term, x minus a, cancels with x minus a. So a is multiplied by the other factor, x plus 1, and b. In the case of b, the x plus 1s cancel, and b is multiplied by the other factor, x plus a. The next step is to evaluate the arbitrary constants a and b. We achieve that by, first of all, we can evaluate a by substituting in x is equal to 8. If we put in plus 8, this factor here will go to 0, and b will be eliminated. We show the plus 8 in red, so we get minus 8 plus 26 is equal to a multiplied by 8 plus 1, so we should get 9 there, and b multiplied by 8 minus 8, so that should go to 0. So the left-hand side evaluates to 18 minus 8 plus 26. That is equal to 9 times a, so we divide across by the 9, and that tells us that a is equal to 2. The next stage is to evaluate b, and if you look up here, you can see that if we make this factor go to 0, we can do that by putting in x equal to minus 1. So we substitute in x is equal to minus 1 to evaluate b. I have the values plugged in here, so we have minus times minus 1. That will give us plus 1 plus 26 will give us 27 on the left-hand side. We have minus 1 plus 1, so a will go to 0, and minus 1 minus 8 will give us minus 9. We divide across by the minus 9, and that will give us minus 3 for b. So this is our formula here. Next step is to plug in the values we just worked out for big A and big B. These constants are a is equal to 2, b is equal to minus 3. The values are plugged in here, as you can see. So we have plus the integral of 2 over x minus a plus minus 3 over x plus 1. These constants are taken outside the integral signs, as shown in this slide also. And now the next step is to integrate the terms. The integral of 1 over x minus 8 will be a log function, the log of x minus 8, the natural log, and the integral of x plus 1, 1 over x plus 1, is the natural log of x plus 1. The next thing is to take these constants up as powers. So we have the log of x minus 8 to the power of 2 plus the log of x plus 1 to the power of minus 3 plus your constant of integration. And because we have minus 3 here, we can bring that x plus 1 underneath. So this gives us our final single log function, the log of x minus 8 squared plus the log of x plus 1 divided by the log of x plus 1 cubed. Thank you for listening.